Swayam Prabha. Digital India. Educated India.
Good afternoon, everyone. Welcome you back to this particular course on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. We have been discussing in the couple of previous classes on the role of XRD, powder XRD, particularly in characterization of the materials, identifying the phases both in the inorganic and nanomaterial aspects of it. So, over the two previous classes we have ran through all the basic concepts related to this, particularly to the powder XRD, which is also known as the polycrystalline XRD. And then we have looked at how to assign or utilize the data that we get from the diffractogram or the diffraction pattern of that. So, one of the methods that we have looked at is what is shown now on this particular slide. Have a look at this. So, we get the 2 theta and the intensities from the diffractometry data, and then you make the sine square theta and sine square theta by minimum sine square theta ratio is 1 into 2 into 3 into etc. Then wherein you can make this into h square plus k square plus l square as a sum of the values of that, and then this converting into the HKL, and using this HKL and the sine theta you can get your A value, which is already known. This is for the cubic phase. It will also show some of the intricate aspects which were missing in this in another workout. So, this is another worked out procedure, how we come out with that total of the h square plus k square plus l square, which is also labeled as small s. These steps are same as what I talked earlier. You have the peak intensity, and then you can divide with this and you can get a relative ratios of the intensities. So, you also have the sine square theta, and you need to find the by integers and find a common quotient and take the value k from that common quotient. So, that is what main part of this particular procedure as compared to the previous procedure. Okay. So, and then we can get the peak line, which is resultant to h square plus k square plus l square. So, based on the pattern of S value, one can identify, already explained you this in the previous class, how to get the Bravais lattice by looking at the reflections which are present and the reflections which are absent. Primarily it is the reflections which are absent are most important. Present could be weak. When they are weak you may not be able to see, but that should not be taken as absence. So, absent is different from the present and weak. So, weakly present. So, that is not the one which is important in crystallography. So, therefore, you need to identify those which are absent absolutely, and those based on the absentee criteria you can work out the Bravais lattice, which I have shown you earlier, and we can see that again. So, using the appropriate formula which I have shown you, again you can calculate the unit cell parameter. So, since I have already talked all this, I may be going a little bit quick, but still I will be covering everything in this. So, here 8 of the peaks were picked up from the diffractogram and their 2 theta value, and you convert into theta and then find the sine squared theta. Then you divide with different integers. So, let us say there is no point in dividing with 1 because it is already there. So, 2, 3, 4, 5, 6, and identify the lowest the minimum value in each of this 0.0361, 0.0361 among all this is the 0.0361, and this is common across all this. So, therefore, this is taken as a quotient. So, that is k value. So, that means you take the sine squared value here, divide with this k. The k in this case has come as 0.0361. So, therefore, the 0.108 divided by 0.0361, that is equal to 3, and 0.1444 divided by 0.0361, that is equal to 4. So like that. So if you do that, 3, then 4, then 8, 11, 12, 16, 19, 20. What is this? This is equivalent to or proportional to the h square, equivalent to h square plus k square plus L square. So, and of course you need to make into the nearest integer, and that's what is made. Sin square theta by k is equivalent to that of the h square plus k square plus L square. Now this is converted into the HKL, and that is what you have. If you look at this particular HKLs which are present, and you will know what are the absent, you can match with what we have earlier. So I showed here, so you can see which are all the present, which are all absent. So in this case it is FCC in this example, because that matches with these ones. So 111, 200, then 220, etc. Those are the ones which are present. But you need to compare, of course, the absences. That is what is done, and therefore this HKL pattern is FCC. Now if you use any of these, each the 2 theta case, you can get the corresponding D value, and then you can get corresponding these A values also. But here you just shown one of the A value is given. Okay, so that is how one can work out the procedure. So the indexing, obtaining the lattice parameters, etc. I hope got it. And if you do it on your own, taking one of the example, and that becomes you will never forget, you will completely remember in that kind of things. So here again, the maximum frequency of this is the 0.0361 among the lowest figures, and that is why that is being picked up, and that is what is highlighted here. And you can also see whether you are getting the integers or not. With respect to that, you are getting very close to the integer, 11.001, etc. So therefore that is the correct kind of thing, and you get the total sum of h square plus k square plus L square in that. Okay, so I hope with the procedure which I showed you in the previous class and the procedure I have shown you just now, together I'm sure you have now confidence in tackling some of those. But when you're doing it, just try with the cubic systems, because that is most simpler. And other things anyhow, as I mentioned, can be used, can be done by the computer methods and that. Yes, whatever I mentioned earlier, that the other tough cases can be done by the programs, it's called auto indexing. So whatever you have done, that was the manual indexing using all these calculations of that, then auto indexing is basically done by the software. Okay, so this is much easier. Of course, you've seen that it is very easy to index for cubic only. But if you go to little higher, somewhat okay, hexagonal, rhombohedral, somewhat okay. But there is a lot of additional involvement of the time and the arithmetic that is being needed to be done. But however, if you go lower than that, so something like a orthorhombic or triclinic or monoclinic, these kind of systems, then you require much laborious process, because you've seen earlier the kind of the formulas involved in them. Here you can see all the D, because you need to get the D. Without the D you can do nothing. So therefore huge amount of formulas are involved in all these things. So therefore it becomes very laborious making all those things. You need too many iterations to get that minimal k value and those things. In principle it can be done, but there will be a lot of tedious thing. So in such kind of things, one can recommend the researcher or a student to go through this auto indexing process. So auto indexing is available in all the crystallography based softwares, and the diffractometers have got this software, and that software has all this. But one has to be a little bit cautious. When do one go for this? When the crystal system symmetry is lower than the cubic, just now I mentioned. When the data is huge, but a lot of reflections are not very intense, and thereby may not be very accurate, because low intense reflections measurement will be somewhat less accurate. What it means is, so that is where data may be huge, the intense reflections are very small. So when a sample has some impurities, why? If impurities are there, you have the main sample, its diffractogram, or its the reflections, as well the impurity reflections that you will get. So there is some of them, they may overlap, they may add it up, etc. So a lot of troubles are there in that. So in that case, the peak profiles resolving will not be happening by manual. That can be done somewhat better by using certain kind of a resolution parameters by using the programs. That's why you go for the auto indexing. When the symmetry is not very accurate, there is some kind of a pseudo symmetry is being present. So in that case, again, manual way of indexing is not very easy. So unit cell dimensions which are close to a higher symmetric part of the fitting, better to be taken, the higher symmetry be accepted. You always need to see in the powder diffraction at least 15 to 25 peaks which are strong ones, which are somewhat higher in theta value. So strong one, intensity should be good as well as the higher in theta. The greater the higher in theta and the better the intensity is the best in terms of your indexing. So that is where you don't find that many number of reflections in the powder data. This is not a single crystal. In single crystal you will get some thousands of reflections, of which several hundreds are very strong. Okay, so this is another aspect why you go for auto indexing. So of course when you use the computer based programs and go for the auto indexing, it gives a large number of outputs, not that one. So you need to look at the output. It also gives, the way it is done, it calculates how good that could be, how good that's proposition of that indexing, another indexing, another indexing. Suppose it is given 3 or 4 indexing, so they are put in the order of figure of merit, and the best figure of merit and the next one may have a parameters which are reasonably close to that of the correct ones. Okay, so these are the reasons why you go for auto indexing. And what is auto indexing? When do you do it? How do you do that? All those things are there. How exactly is not shown in this, and this will be there in the program itself, because there are a lot of parameters are being introduced into that. So now the indexing procedure that I showed in this class and the previous class were the manual kind of a doing. This is quite good for the cubic, to some extent okay for hexagonal kind of things, but preferably to go for the auto indexing at lower. But one has to exercise a caution. Okay, the reason is that we have seen huge number of formulas are involved. If some error is there in any of those, then whole thing will go haphazardly. Now I've already explained to you by 2 means or methods of finding the lattice parameter. Now we have a method here given to get the precise lattice parameter, and lattice parameter can be obtained for each HKL value. See here. So HKL, one of the HKL, A value, second, third, A value is the same because it is the same unit cell and same lattice. So but the value will be slightly different. So in that case here I have shown the average, but there are ways and means by which you can get the more precise value. Average need not be a precise. Average could be some good figure but need not be the precise value. So that is where I am talking about now with the method which is used for getting the precise lattice parameter. So here what you do is, because you have in your powder has got a particles. The particle could be a polycrystalline within itself, or it could be single crystal also, and particle sizes will also change, could also change from. So there will be a huge distribution of that. So that is why I have some errors coming up in the measurements that you have based on one HKL, based on other HKL. So based on HKLs, so each HKL, so that means H1, K1, L1, you will get A value. H2, K2, L2, you will get A value. But you will get some variation in this. So what I showed earlier was to take a kind of an average. That will give a better value, but not the precise value. So for the precise, what I have given was here, which is quite popularly used, and this is developed by Nelson-Riley function. So what you do is, you use the cos square theta by sine theta plus cos square theta by theta as a function of the lattice parameter A that is obtained for each of the reflection, and that is what is done, and that will take care of the distribution of the particle sizes that you have and the nature of the particle, whether they have polycrystalline and single crystalline things. So this is done for 4 different particles of low, 0 means not the 0 basically, it's into the basically nanometer size, then 100 micron, 200 micron, 400 micrometer sample, and for each of these you do several reflections. So you can see 1, 2, 3, 4, 5, 6, and you try to make a best fit and such that it hits here 0. So that means the 90. So because cos 90 will be the 0. So therefore you're getting at 90. 90 is the maximum level of reflections that you can get. So it's extrapolated. So it's basically, so it's done for one size. Diamonds are done for the basically for this very low size, and the squares is done for the 100 micron, and triangle is done for the 200 micron, and the X symbol is done for the 400 micron. You can see, but all of them they're trying to here. Now if you require, still you can do, but more or less these are all converged here. And if you go and check this value with whatever is published, you will find quite well matching that. So how this is done, etc., its basic concept is given in this, but which I explained already. Okay, so you have to find the A value for each of the reflection at different size. That is what is called sample displacement parameter. So that different sample displacement, which means the different size of the samples. Okay, so those which are lower than the micrometer, you just make it, but it doesn't mean the 0 kind of thing. So now you get how one can get the precise lattice parameter. You have the lattice parameters, but you need to get the precise, otherwise you take the average of that. And there are other methods also there called refinement. Okay, so one can use certain refinement parameters and try to get that as well, which I have not shown in this because it's not very important. Now let us look at, so overall we have now looked at the how a diffractogram comes like a cone, and when you open the cone it becomes a strip with the 2 holes in the vent, because one is input radiation, other is exit radiation, and that, but now you don't use that at all. You use completely the diffractometer to measure the radiation detector straight away without using any kind of films. So what do you get? What is your raw data? So raw data is you have the position, which is called in terms of theta, and the intensity in terms of the counts, in terms of the area. So these are the things. Now, and this information is plotted into a digital, into the analog, and gives you both. You will get this soft copy of this data as well as this one as well. This is to visually you can see which is high, which is low, at what peak, and can immediately identify, compare, those kind of things can be done. The next task, which I already explained to you in the previous class and this class, is working the DHKL and working the relative intensity, working out the HKL. So all of these, the HKL, DHKL, relative intensity is that intensity of that peak divided by the intensity of the highest intense peak. So that is where you make it. And if you want percent, multiply by 100. Okay, so that means you have very weak peaks, very strong peaks come closer to 100 side, and very weak peaks comes closer below 5, below 10, etc., etc., and you have a huge number. That is where you need to choose. Second thing is you need to choose based on the higher side of the theta, and these two will be helping a lot in this. So these are the kinds of data. This is called the reduced data, this is called the raw data. So this is the DI data, that is DHKL, and then intensity, that is DI data. So the diffraction data is reduced to peak positions and intensities. This is used to derive the family of planes. You can get that Miller indices. I have already shown you the family of planes in the past, in one of the previous class, in the first class itself. Though individual plane cannot be resolved, but this can be resolved in a single crystal. It's not single crystal, because in a powder you have so many single crystals, but oriented in variety of ways. That is called polycrystalline or powder. So one of these thing will maybe cancelled by the other, etc. You get only few. That's why you get much less number of peaks in the diffractogram with the powder or with the polycrystalline material as compared to a one single crystal. One single crystal. That will be completely aligned. So all the reflections you will get quite well. So that is how we have. And let us look at a few little other pieces of information in terms of application wise. Okay, so here as I mentioned earlier, you can also identify impurity. Impurity means a mixture. You have some compound A, you have a small amount of B. So, so that means a mixture is a mixture of A and B. So can we get yes, you can. So for example, here on the left side, I draw your attention to this slide, and you have a quartz, you have a cristabalite, and these peaks are different from the blue peaks are different from that of the red peaks, and then you have a glass. And now you take a mixture of these things and look into here the XRD. You can see this. If you take this, you got that. You see these blue peaks. This is one of this, and this is one of this. This is one of this here, and this. And for this red one, you can see here, and you can see here, and you can see here. So all of these. So it is just a mixture of that. Luckily, they are not overlapping one over the other. Therefore, from the areas, you can find out how much you have mixed these things. So conversely, you can do that. So that is how you can find. If they have exactly overlaid, it's very difficult. If it is like a shoulder, then you can use some programs to deconvolute and then get the areas of that. Another example where this is a diffraction pattern of the platinum nanoparticles which are mixed with the silica. Your platinum powder is mixed with the silica matrix and then slow. So if you look at the platinum alone, very nice sharp peaks you have. Now this nanoparticle mixed with this silica, then you see, but silica does not show because there is a completely amorphous. It's only platinum. So the platinum peaks are still retained, but in a little different manner. This intensity is lower, this is higher, whereas this is higher and this is lower, and the ratio is also different. So that basically talks about you have made kind of a composite when you mix the platinum nanoparticles with that of this one. So it's but you can identify, yes, the platinum is there, platinum nanoparticles are there, but may not be in the same form as the platinum sheet, but in an entirely different form of that. You can also look at these variety of examples there, variety of applications of the powder XRD. Here is a system. I hope this is clear here, and this is clear here, a mixture. If you call this as a compound A, this blue one is B, and this is C, this is the A plus B plus C, and you can resolve A, resolve B, resolve C. Therefore, you can get the mixture ratio. Here, it is not that purpose. It is the identity, whether the platinum is there or not in that particular matrix of silica. And the platinum signatures are one here, another here, another here. But the relative ratios, if it is a sheet, platinum sheet, they will be in this ratio. But for this kind of when grounded and made into a nanoparticle with the silica, it is not. The peaks are more or less retained the positions, but the relative intensities are altogether different. And that's what is showing that there is a composite is being formed between the platinum and the silica. And there could be a little bit different kinds of composites in different regions of that in particle. In one particle, there could be one or more things. So therefore, you can get a broad range as well. So in one particle, there need not be one single crystal, and it is never. There is a polycrystalline and maybe several phases or several composites which are present in each. Bulk-wise, if you see, analyze, it will become the same ratio. But individually, that structurally they are different. So you will find that. Okay, let us look at one example of application of powder XRD. So two materials, one is a chitin, one is a chitosan. So again, chitin also is present both in alpha and beta. We'll come to that in a while. First, let us see the chitin, the powder XRD, quite nicely. And this is the chitosan. But this is chitosan with 100,000 Dalton. And this is the chitosan, which is around the 1,000 to 30,000 range chitosan. Will differ. So you have molecular weight based powder diffraction that you can see. Not only molecular weight based, the particle size based also. So in that you cannot say that the particles of this one and the particle size of this one and shape of these are same. No, so they are different. So we cannot just attribute it to the molecular weight, though you can say the variation in the molecular weight has given this, but indeed it is the variation of the molecular weight which reflected in the particle size, particle shape, etc. All of those, particle size distribution, particle shape distribution, all these are important. So that makes that sharper. So now you have a chitin, then you have the chitosan. If you take the chitin alone, alpha will have this line which is the full, and the beta chitin has got this small dots kind of a circles shown that. Okay, they are very close, but some of the peaks are not there. So these ones are there in alpha chitin but not there in beta. This part, these ones, these are all present in the alpha chitin but not in beta chitin. There are two types of the chitin structures of that. So you can see that they are there here, and these are all alpha chitin. So you can make out. Now, using why we are looking at, because these are the materials which you use to make composites. Right? Suppose you wanted to do some kind of a drug delivery, drug nanoparticles embedded into that, or some metal nanoparticles embedded into that to study electronic property or magnetic property. So you can use it as a matrix, you can use it to make the composites. Now look at this is the powder XRD of alpha chitin only, which is this one, but this is isolated from different sources. One of them, number one, whatever is labeled 1, is from the brown shrimp shells. Number 2 was pink shrimp shells from the shells of the shrimps, and third one is crab shells, and the fourth one is crayfish shell. So from each of the shell you can isolate the chitin, and the chitin powder diffractions, primarily their peaks are quite similar, but their intensity ratios and all differ. So here you have a somewhat more resolved, less resolved, intensity ratios are quite different here and quite different here and in this region. Okay, so you can see even here in these ones there is a splitting of the peaks, etc., and these peak intensities are also changing. There are differences, but all of them are alpha chitin, but because their polycrystalline natures differ, that's why you have all this. On this side you have B is the similar source, but it is a chitosan. It's a chitosan which is isolated from brown shrimp shell, pink shrimp, crabs, etc., you can see. Okay, so you can see the peak which is here, not so much prevalent here, somewhat little less, somewhat much less, and you have, so some differences, changes are there because of the polycrystalline nature of these materials are different. Okay, so here is a beta chitin, again from two different sources, cuttlefish pens and squid pens. So this is the one where you have, and this is for the beta chitosan. So this is for the corresponding chitosan. So you can see that depending upon the source of these, where these are isolated, also your diffractogram signatures will vary. This is very important. You cannot have that. So, but that particular phase can be cross-checked in the literature and make these ones in all of these. Okay, so what we are trying to look at is, after having gone through the exercise of identifying and indexing, etc., getting the A parameter in the previous examples, we have now started going through some application aspects of this, and particularly to nanoparticles or composites, and this, of course, you can get large number of examples even for the inorganic compounds, coordination compounds, all those things, they are available. As you said, more than 1.3 or 4 million data is available on the source. Okay, so I will come with additional examples in the next class as a continuation of this, particularly in terms of how the powder XRD can be used in various, and maybe I will also bring some pieces and bits of information where one needs to be very cautious with all the data cannot be, because of the size of variation, polycrystallinity variation, shape variation. These are very important parameters. Cannot assume that everything is fine just because of that powder, of that particular material. No, it is not just the molecular level, it is at the grain level. So, the grain characteristics are important or particle characteristics are important. Thank you very much.